Okay, so recording has started. So welcome back, right, to another week. As you guys have already seen, you might have seen, we have our first exam coming up next week, right? So please, I've already uploaded the study guide, right? So please check it out as soon as you can, at least start solving them, right? The Math Center will have a review session for you guys. And then you probably have a review before, like on a Tuesday, the recitation on Tuesday before the exam on Wednesday. But it would be a good idea to start looking through the study guide, which I've already posted. So you find it under the file section on Web Campus, on Canvas. Okay, but before we start, please, do you have any comments, any issues or concerns that you need me to address? Okay, so the last time we were looking at, so let me go here. Let me share this. So I'm sharing the whiteboard now. If you can't see, please do let me know. So the last time we were looking at this function, right? And we were trying to find we were asked to find the horizontal and vertical asymptotes, right? So let's just see how this is going to look like. Now you encounter a similar problem like this on tomorrow's quiz. So let's start with, so we started with vertical asymptotes. Right, so we said for vertical asymptotes, if you are given the function, then the candidate is, you have to look for where the denominator, what makes, if it's a quotient, right? If it's a function over another function, then you have to look at what makes the denominator 0, right? So that'll be the candidate. So you set 3s minus 5 equal to 0, and that'll give you s equal to 5 over 3. And when you get this value, you're going to do like one-sided and check if it's an infinite limit. If this gives an infinite limit, then s equal to this is a vertical asymptote. Right, so I think I asked you guys and we agreed on this from the right. So you're going to do from the right of this function. So I have 2s squared plus 1 square root of 2s squared plus 1 over 3s minus 5, right? So we are just trying to find this limit to see if it's an infinite limit. So what do we start with? Well, we start by trying to plug in, right? So we plug in. So what are we getting? We are getting square root of 2, and then this one is 5 over 3 all squared plus 1. And then all over what? 5 over 3 minus 5. Now this is giving us this 25 and then over 9. So 25, that's 50 over 9, and that's 59. So that's 59 over 9. So something like so, all over 0, right? So when you plug in, this is what you're getting. But then with this number that you have here, you have a non-zero number over 0, right? So how do we get the actual limit? Well, we have to just look at the kind of values that this is taking on. And then, so we know for sure that this one will give us an infinite limit. It's one-sided and it's a non-zero number over 0. But which kind of infinity is it? So to check this, we just have to evaluate or analyze where this is approaching from, and then see where the 0 will be approaching from. Whether it's it's approaching 0 from the right, in which case it's kind of like a 0.00001, or it's approaching 0 from the whether it's approaching 0 from the right, in which case it's positive 0.0001 of some sort, or it's approaching 0 from the left, in which case it's a negative 0.0001, right? So with that, I'll need to move on to the next slide. Please do let me know if you need more time here. Okay, so moving on, that means for this one, we just have to track the 5. I should perhaps write this thing back here. So we have limit as s approaches 5 over 3 from the right, and then the function is square root of 3s squared plus 1 over 3s minus 5. So let's just check 5 over 3. You're approaching from which side? From the right. So which kind of numbers are to this side? Now, because you guys are not allowed calculators on your test or quizzes or stuff, and to re-emphasize that idea, I'm not going to use a calculator, but let's see how best we can analyze it without using a calculator. Well, if you're looking at 5 from the right, then a very close number to pick is something like a 5.000001 over 3. Please, I hope you agree with this. Right, this is a very fair number because you just need to check for the numerator maintain the same denominator, and then you get this to be very close. So there's a kind of value, a number that's to the right of 5/3. Right, so let's analyze that inside here and see what's happening. Right, so now if I should try and analyze this, let's see what's going on. So putting this here, if you have 3x, where the x is something like, it's taking on values like this, 0.00001 over 3, and then minus 5. I'm just doing for the denominator so that I see which side of 0 is approaching from. Then that means that you have a what? The 3's will cancel out, and you have something like a 5.00001 minus 5. So that means that the denominator by itself is approaching 0 from the right, because all of this calculation that you're doing here will give you something like a 0.00001. So it's approaching 0 from the right. Right. So with that idea, you can see that this is a positive number up here. Remember that we got square root of 59/9, but it's a square root, right? It's a positive square root. So that means this is a positive number, right? You have a positive number up here divided by 0.00001. Yeah, and with that, can anyone please tell me what the answer is? What will be the answer to this? What is this limit? So I have infinity. Thank you. Thank you. Perfect. I have a seconder. Awesome. So that's going to be infinity, right? So we just shown that taking this, looking at the limit as s approaches a 5/3 from the right is giving us what? An infinite limit. Hence, we can conclude. So maybe, let me see. Because limit as s approaches 5/3 from the right of this, we conclude that the vertical line x equal to 5/3 is a vertical asymptote. Please, are you okay with this? Any questions here? And don't forget, for vertical asymptote, you just need to check for one of them. Even though there are 6 ways it can go, you can have like limit from the right and from the left, like the two-sided giving you a positive infinity or negative infinity, or the one-sided giving you from the right, one-sided from the right, giving you a positive infinity or negative infinity, or one-sided from the left, giving you a positive infinity or negative infinity. So there are 6 possible cases, but I just need at least one of them to be true, right? Just one of them. So we just showed it for one. So that's it. We have this to be our vertical asymptote. Now, this happens to be the only candidate that we found, right? So that's it. We are done for vertical asymptotes. Please, any questions on vertical asymptotes, how to find them? Okay. So I'll need to move on to the next slide to look at the horizontal asymptote. Let me know if you need more time here. Okay, then let's proceed. So for horizontal asymptotes, from the last time, we learned that for horizontal asymptote, we need to look at what? Limits at infinity, right? Limits at infinity. So for that one, the 2 principal ones are the limit as s approaches infinity of the function and the limit as s approaches negative infinity of the function. So these are the 2 you have to check. I think I see something in the chat. Okay, hi there. Sorry. Oh no. Okay, sorry to hear about that, but welcome back, right? Welcome back to the class. Yeah. Yeah, if you missed anything, feel free to reach out after the class. Or if you want to talk about any other stuff that you missed. Okay, cool. So now let's continue. So we are looking at these 2 limits, right? So let's do that. So we start with the first one, right? So we take the limit as s approaches infinity of the function. So you have square root over 2s squared plus 1 over 3s minus 5, right? So let's take this limit at infinity. Now for this one, we said that when you're trying to find limits at infinity, and then you're looking at a quotient function, a function over another function, then what you're going to do is divide by the greatest power of x in the denominator, right? Divide by the greatest power of x in the denominator. So looking at this, what is the greatest power of x in the denominator? What do you say? What is the highest degree of the greatest power of x? Perfect. I have one. Oh, I just said perfect. So I think that's, yeah, but I have second that's perfect. You guys are awesome, right? So the greatest power of x in the denominator is just 1, power 1, which means you are just going to divide both sides by x, right? So we are going to divide the numerator expression by x to the power 1, which is just x, and then also divide the denominator expression by what? X to the power 1, which is x, right? So that's limit at infinity. If it's a quotient, then just divide by the greatest power of x in the denominator, right? Okay, so now with that, okay, yeah, that's a good question. So someone is asking, can we use the shortcuts you told us? Yeah, the shortcuts are solid, like they are perfect for rational functions. If it's a rational function, it's perfect. It's foolproof. It always works. But for this one, you have to be cautious. If you're going to use the shortcuts. The shortcuts are not always direct like the ones I gave. That's why I said for the shortcuts, it has to be a rational function, right? If it's a rational function, and then the limits at infinity, the shortcut will be foolproof. And you see what I mean very soon. Now let me show you a bit of it here. Now using the shortcut, let's see what is going to happen here. Technically, this is not a rational function, but let's see if we can kind of like figure out the degree of the numerator. What is the degree? Like a degree. I'm putting it in quotes because this is not a rational, this is not a polynomial. The numerator expression is not a polynomial. But then the kind of degree we get here is something like, yes, 1, perfect, right? As you can see, this one is 2s squared. So if you take the square root of 2s squared, you're getting a degree of something like 1, right? So something like a degree of 1. You see, it's good you asked that. Let me erase and write it well. Let's say degree 1. Right? What about the denominator? What's the degree? The denominator expression is also what? Degree what? 1. So you are taking a limit as you approach, you are taking a limit at infinity, and the degree of the numerator is 1, and the degree of the denominator is also 1. That means that the limit, the answer will be what? A quotient of their leading coefficient. So here, the leading coefficient is square root of 2, and the leading coefficient down here is 3. And this will be true. This will be correct. It will be perfect. So the shortcut will work for this. Right? But as you see, when you do it for negative infinity using the shortcut, you have to be careful. So sometimes the shortcuts, so that's what I'm saying, the shortcuts are foolproof for rational functions, but for other expressions, it's tricky. It may work for some conditions and not work for other conditions. So this one, it will work for limit as s approaches infinity. The shortcut works. This is the answer that we're going to get. But when we get to negative infinity, you see what I'm talking about by it can be tricky, right? So the shortcut will work here. So that's our answer. But let me do it for when I'm done, I'll do it for negative infinity. And you see there, you have to be careful there. So now let's continue from where we left off. So we are here, right? Now for here, you're trying to simplify this expression as best as we can. But then as you can see, this x that you have down here, right? The x that you have down here, we need to be able to cancel this 2s squared plus 1 somehow. We have to reduce it because the target is we want to reach something like a limit as s approaches infinity or negative infinity of some kind of 1 over x power, right? Because we learned that limit as a s to the power, s approaches infinity of 1 over s squared is 0. Do you recall? Because so if we get some terms like this, then we can just reduce them to 0 and then everything will come out just fine. But then there's an issue here. This s here cannot reduce this directly. But there's something we can do to this x so that it can move underneath the radical symbol, right? So remember that if you have x, if x is positive, then x is the same mass as square root of s squared, right? So think about it. For something like 10, right? So example, if you have something like 10, then 10 is equal to square root of 10 squared. And don't forget, as we approach infinity, the x is taking on positive values. So every positive values is every single positive value is equal to the square root of a square, right? So 10 equal to square root of 10 squared, right? A billion equal to the square root of a billion squared, and so on and so forth. So that means that we can just replace this x with what? We have the limit as s approaches infinity of square root of 2s squared plus 1 over square root of what? S squared. Right? Now let's just simplify the denominator expression. So that one is 3s over x minus 5 over x, right? And then moving on, because now I have a square root here, right? Recall that if you have square root of a over square root of b is the same as what? Square root of a over b, right? So with that, we can say this is limit as s approaches infinity. And I have square root of what? So 2s squared plus 1 over s squared. And then down here it's just 3 minus 5 over x, right? And so moving on, now that this s squared is underneath this, we can simplify this, right? So we get something like limit as s approaches infinity. And then square root of what? That's 2s squared over s squared plus 1 over s squared. So that'll give us 2 plus 1 over s squared. And then all over 3 minus 5 over x. Please, are you okay up to this point? Any questions? Okay, so now that we have everything set up, don't forget this is usually the goal when we are looking at limit at infinity, right? The goal is to get some form like this, like something over x, so that one will go to 0, right? So for limit as s approaches infinity of 1 over s squared, that will go to what? 0. The limit of a constant is the constant. The limit of a constant here is a constant, right? And then this one will also go to 0. So in the end, we are going to have something like square root of what? 2 plus 0 over 3 minus 0, which is square root of 2 over 3. Right? Like we had for the shortcut. Please, are you okay with this?
Wait, so is that second equation below our original one like an example, or is that like continuing on?
Which one?
The square root of 2x squared plus 1 over x.
2s squared plus 1 over x. Square root of 2s squared plus 1 over 2s squared square root of 3. Is it this one? Wait. This one?
Yeah, it's the
Let me see.
The one directly below where you have the degree 1 over degree 1.
Oh, this one?
To the left of that.
This one?
Yeah, I'm not sure where that came from.
Let me see. Okay, for this one, right?
Yes, that one.
Can you see you can see my pointer, right?
Yeah, I can.
Okay. So you mean this one, this step?
Yeah, that's the one.
Okay, cool. So for this step, what you're doing is we are trying to take the limit as you approach infinity. It's a limit at infinity. And for limit at infinity of a quotient function, right? Something divided by another thing. We use the highest power of s in the denominator and divide both expressions, the numerator expression and the denominator expression, by that power, right? So here, looking at the denominator, right? The 3x minus 5. The highest power of x down there is 1. Is x to the power 1, right? So we use that x to the power 1 to divide the top expression, which is square root of 2s squared plus 1. So we divided that by x, and we also divided the denominator also by x. You see, and I've not changed the expression, right? Because remember, if you have like a fraction, say 2 over 3, and I multiply the 2 by, say, 1 over 2, and I multiply the denominator also by 1 over 2, I don't change the fraction. It's still going to be the same thing.
Oh, okay. I see what you did now.
See? Yeah, so yeah, nice. So that's how come we're able to.
Thank you for explaining that.
Sure, you're welcome, Shane. Okay, so up to the final answer, please, do you have any questions? Okay, so that's our final answer, which is the same as a shortcut. Now, we can conclude from here that because the limit as you approach infinity is this, we can conclude. I'll need to move on to the next slide to write that. So do let me know if you need more time. Right, so the limit at infinity is giving us a number. So we can conclude, right? Hence, we say the y equal to that is a horizontal asymptote. Okay, so we did it for infinity. Let's try negative infinity. Now, if it was a rational function, which is a polynomial of a polynomial, then the limit as you approach infinity and the limit as you approach negative infinity will give you the same answer. So for that one, you don't need to go through the stress of working out the limit as you approach negative infinity. But as you can see, this one is different. This one is not a rational function, right? This is some radical and then divided by some polynomial. It's not a rational function. So let's try that one too. So we try limit as s approaches negative infinity this time. And then square root of 2s squared plus 1 over 3x minus 5. So please, for those who are fans of the shortcuts, now I want to test you here. Please try and write out what you think the answer to this is using the shortcuts. And then I'll show you that you have to be careful when you're using the shortcuts, especially for non-rational functions. So please type it out. I'll just be working the usual approach by trying to use the shortcut to give me the answer here. And then I'll show you something. So not using the shortcuts, I'll say, okay, so there's a limit as I approach in negative infinity. This is a quotient function, a function over a function. So let me look at the highest power of x in the denominator and divide each expression by that. So the highest power of x in the denominator is what? Is just x. So I'll do something similar to what I did previously. So I have this square root of 2x squared plus 1 over x over what? 3x minus 5 over x, right? And then at this point, let me say this. Anybody done with the shortcut thing? Can anyone figure out the answer using the shortcuts? Or no one tried? Okay, maybe let me do this. Let me help you guys figure that one out. So using the shortcut, you say, okay, what is the degree of the numerator? So help me out. Okay, so we are saying same as the other HA. So I'm thinking you guys think is square root of 2 over 3, right? Is that what you are saying? Is that what you think? What do you say? You think it's square root of 2 over 3? Okay, using the short, yes, that's what I wanted you to conclude. That you may think that the degree of the numerator is, I'm putting the degree in quotes because this is technically not the degree, but the degree is like a square root of a s squared, which is 1. And the degree of the denominator is also what? 1. So you match the leading coefficient, which is 3 in the denominator and square root of 2 in the numerator, right? So you say that is this. But in this case, this is incorrect, right? This is incorrect. And you see what I mean by that here. There's something technical happening here. Now, remember that if you have, we want to reduce this, we want to simplify this radical using the x. So we need to create something like a square root here. But unlike the positive numbers, right? Recall that if you have 10, it's the same as the square root of 10 squared. But the issue is if you have negative 10, it's not the same as square root of negative 10 squared. Because square root of negative 10 all squared will give us square root of 100, which is 10. 10 is not negative 10. You see, so for negatives, this is the complication. You can say x is equal to what? Square root, positive square root of what? S squared. Why? Because the x is taking on negative values, right? This one, the limit as s approaches negative infinity, is taking on negative values. So we have to find a way around that. So what do? Well, notice that if you have square root of, if you have negative 10, then if you want to get the same negative 10, you have to negate the square root of what? Negative 10 squared. If you do that, then this negative will be waiting out here, whilst this returns a positive. So you end up with what? Negative 10. Right? So that means that whenever the x is taking on negative values for the limit, this x, if you want to include a radical, right, which is a square root, you want to change it to something like a radical, then this has to be negative square root of what? S squared. Please, I hope that makes sense. Okay, so if that makes sense, then that means that now we are here. You have limit as s approaches negative infinity. So maybe let me add this so that no one knows. Wrong here, wrong. In this case. I mean for this. So that means you're going to have square root of what? 2s squared plus 1 over the negative square root of what? S squared over what? The denominator will still be the same. So that's 3 over 5 minus 5 over x, right? And then moving on, you're going to have the limit as s approaches negative infinity. And then I have negative, and then we pretty much get something similar, right? So the s squared can go underneath this. So we have 2s squared plus 1 over s squared. And then all over 3 minus 5 over x, right? And then still moving on, everything simplifies to limit as s approaches negative infinity of negative square root of 2 plus 1 over x squared over 3 minus 5 over x. So at this point, we employ the building blocks that we talked about, right? So this limit The limit as s approaches negative infinity of r over s, that will go to 0. And this will also go to 0. So that means we finally have an answer of what? Negative square root of 2 over 3. You see? When you use a shortcut, you may miss the negative, right? The negative is missing here. That's why I said you have to be cautious. So that's just illustrating that. So here, in this case, we have two what? Horizontal asymptotes, right? We have y equal to square root of 2 over 3, and then y equal to negative square root of 2 over 3. Please, any questions here? Is there any part of the calculation that you don't understand? Okay. I need to write the thing here on the next slide. So do let me know if you need more time. Okay, so, oh, I see something. So if you wanted 2 for positive values, you can use. Yeah. For negative values, you can still modify the shortcuts to say that, well, if you're taking the limit as s approaches negative infinity, then you have to be cautious of it being possibly a negative there. Do you see? So maybe you can modify the shortcut in that sense. Yeah. So I can say, hence, y equal to negative square root of 2 over 3 is a horizontal asymptote. So there are two horizontal asymptotes here. Right? So that's all on this. Please, any questions here? Are you okay? Yeah, so that's how you solve it. Okay. And let me go back to the PowerPoint. So the PowerPoint will have, no. Yeah, so the PowerPoint will just have nice ways of, like, it will have explanations and like nice ways of, nice notes. Right, so for here, we started, okay, they started with taking the limit at infinity. They started with positive infinity. Divide each by x. And then square root of s squared is x for s positive. So it becomes this. And then it simplifies to this. And then you know by the limit laws, the limit of a radical and then the radicand is just the square root, like the radical there, and then you have the limit of what is underneath, right? Which is the square, the radicand. And then you take that one, that will be the limit of a sum, right? Then you get this. Then the limit of a constant, that's just 2, and then plus this one will go to 0. You have 3, limit of a constant, this also going to 0. So 5 times 0. So in the end, we have what? Square root of 2 over 3. So that means that y equal to what? Square root of 2 over 3 is a horizontal asymptote of the graph. On the other hand, you have to also need to remember that if it's approaching negative infinity, then the square root of this is negative x, right? So for this one, it's just trying to tell us that as you approach negative infinity, right, the x here is not just x, it has to be negative square root of s squared, right? So that we get it, just like I explained, right? So everything reduces to this, which gives us the final answer of this. So we conclude that y equal to negative square root of 2 over 3 is also a horizontal asymptote, right? So for vertical asymptote, which is what we did first, you have to, since it's a quotient function, you find candidate by setting the denominator equal to 0 and figuring out one-sided. I think for this one, they also happen to do from the right. From the right is giving us an infinite limit. Hence, s equal to what? S equal to that. Okay, they did it from the left. But as I said, you just need one of them, right? So they got a final answer of s equal to 5 over 3 to be what? A vertical asymptote. Now, this is the graph of what's happening, right? Please, any questions here? Okay. So then let's move on. So that's it for vertical asymptote, horizontal asymptotes. Now we are coming to the next step, which is infinite limits at infinity. Infinite limits at infinity. Now we've already learned about infinite limits. And we also know about limits at infinity. So infinite limits at infinity is just a combination of the two, right? So for this one, you have these kind of 4 structures. You can either be taking the limit as s approaches infinity. So that makes it a limit at infinity. And then you are getting an infinite, right? Something like you are getting an infinite number, like negative infinity or positive infinity, right? So you're taking a limit at infinity and it's giving you infinity or negative infinity. That's what we call an infinite limit at infinity, right? A combination of those two. So there are 4 ways you can get this. Either you're taking s approaching infinity and you're getting infinity. Either you're taking the limit of f of s as approaching negative infinity and you're getting a positive infinity, or you're looking at the limit as it approaches positive infinity of the function and you're getting negative infinity. Or lastly, you're looking at the limit as it approaches negative infinity of the function and you're getting negative infinity, right? So you see a merging of the two. The result is an infinity, a kind of infinity. And then the limit is what we are approaching an infinity. Hence is what a limit at infinity. So that's a combination, just merging the two. Please, any questions here? So those are the 4 structures for infinite limit at infinity. Anybody needs time here? Okay. Need time? Let me see. Okay, sure, Lena. Let me wait a couple of seconds. You're done? Okay, you're welcome. So now let's go. So let's look at some examples. So with that one, we're looking at example 5. So let's try and find this limit, right? So for here, the graph will be provided on the PowerPoint, but let me just show you how you could analyze this, right? So for this one, let's look at the first one, limit as s approaches infinity of s cubed. So think about this. If you have a very, very huge positive number, and then you take the cube of it, then that means you're going to still end up with a very huge positive number. Do you see? Because something like 10 cube is going to give us 1,000. 100 cube is going to give probably like, so that's like 6 zeros, right? So that's like a million, right? And so on. It's going to be a positive, a very, very big number. So you can just analyze that and kind of like think around this and see that this is just infinity, right? In other words, this is not a proper way of writing this, but you can say, in other words, infinity cube is infinity, right? So there you have it, right? What about as you approach negative infinity? So that one, to think about it. For a negative number to the cube, so something like, since the power here is odd, if you put a negative number, it would still come out as negative, right? So something like negative 2 cube is negative 8. Negative 3 cube is negative 27. It will always come out as a negative because the power is odd, right? But then when you look at the other one, the other side, what about the infinity part? We know that for infinity, if you take the power, it will still approach infinity. But then you have a negative here, so that's also going to be negative infinity. Please, I hope you see that. So in other words, you can say negative infinity cube is negative infinity, right? Yeah, so that's the answer. So these are examples of what limits at infinity. So the notes is just telling us that if you look at the pattern, for 10 cube, we get 1,000, 100 cube, get a million, and so on, right? For each of these cases, it's becoming unbounded. It's just becoming big. So we conclude that what? The limit as s approaches infinity of s cube is just infinity, right? Okay. Anybody needs time here? Okay. Now, the same holds for the negative infinity, right? For a negative number, if you plug in here, you get negative infinity. You can also try and look at this, looking at the graph of s cube, right? For s cube, if you use the graphical technique, as you approach positive infinity, right, you can see that the graph is going up unbounded. So that shows that it's going to be infinity, right? So the limit as s approaches infinity of s cube is infinity. You can just use the graph to see that. Or as you approach negative infinity too, you see that the graph is going down unbounded. So that also implies that the limit as s approaches negative infinity of s cube is negative infinity. So either the graphing way or thinking about the kind of numbers that you're plugging in, you still get the negative infinity or infinity. But in either case, is what? It's an infinite limit at infinity. Okay, any questions here? Anybody needs time? Okay, now let's look at some other functions which are infinite limit at infinity. Now, one example is e to the x, right? As you can see, for e to the x, right? If you look at the graphical technique, as you approach infinity, right, then this one is going up without bound. So we conclude that the limit as s approaches infinity of e to the x is what? Is just infinity. On the as you approach negative infinity, that one, it doesn't happen, right? As you approach negative infinity, this time it's not an infinite limit at infinity. This time you're getting what? Limit as s approaches negative infinity of e to the x is 0, right? So that one, y equal to 0, will be a horizontal asymptote. That one is different, right? But the kind of infinite limit at infinity is this one, where you're approaching an infinite number and then you are getting something infinity. So these are just examples. Please, any questions here? Anybody needs time? Okay, now let's look at the last example under this section. So for this one, let's try and see how you're going to do this, right? So let's try and plug in and see. For this one, you have s squared minus x, right? I'll show you two ways of doing this. So when you try and plug in, you have something like infinity squared minus infinity. Infinity squared, we all know is infinity minus infinity. The question is, what's infinity minus infinity? What is infinity minus infinity? Anybody? So good. So I have 0, infinity, 0. Yeah, that's good. So this is a form which you call indeterminate. Indeterminate. This is an indeterminate difference. And we talk more about this when we get to 4.4. The thing is, you can't determine. Yes, it depends on which infinity is. Perfect. That's true, Thomas. Thank you. Yeah, that's true. So the thing is, not all infinities are kind of similar. If some function, infinity is not a destination, but some approach it at a faster rate than other functions. Some functions approach it faster than other functions, right? So in this case, if this function, right, if you just have infinity minus infinity, the reason why it's indeterminate is it's possible that this infinity part one is increasing faster than the last infinity, in which case this one will be reaching infinity at a faster rate. So that means that in this case, this infinity minus infinity will be infinity. Or is the other way around? Maybe it's the second function which is increasing faster, in which case it will come like, it will kind of like overcome the first one, in which case the answer will be negative infinity. Or the two kinds of infinities will be close enough, right? They are increasing at a kind of similar scale, in a sense that when you subtract them, you get a number, maybe 0 or maybe a constant, right? So that's why it's indeterminate. You can't tell, right? So what do we do? Well, let me teach you two approaches. So one approach is you can just look at the functions involved, and if you have knowledge of how fast they are increasing, then you can tell what the answer is, right? So for s squared, a quick sketch shows you that s squared is like so. What about say y equal to x, right? Now you're interested in the tip, right? So maybe y equal to x will be something like so. Let's look at the ends as you approach infinity, right? At the end, you see that the s squared is standing up like so, and then the y equal to s is like that. So the s squared will be moving faster than the x, right? It will be moving faster than the x. So that means that this infinity is kind of like approaching faster for s squared than the x. So in that case, the answer is what? It's just positive infinity. Or you can do this. So method 2. This method 1. So just think of the functions involved and then analyze. Let's look at method 2. So for that one, if you get an indeterminate difference, all that you have to do is simplify, try some simplification which will work. So try and simplify, and analyze again. That's the trick. So what do we mean? For this expression, the only simplification that comes to mind is to factor. That's the only thing. If it involved radicals, then the only simplification will be to rationalize. So in this case, because the only simplification that comes to mind is to factor, we just do that. So we are going to factor out an x, and that'll give us x minus 1. So now let's try again. So let's analyze. So if you have the limit of a product is the product of the limit, right? So let's try this one. So that one for x, it will just be infinity. You have something like infinity minus 1. But a very, very big number minus 1, the 1 is not going to affect it anyhow. So you are going to end up with something like infinity times infinity. And what's a very big positive number times a very big positive number? It's still going to be infinity. So in either case, you get the same answers. Please, any questions here? Hope this makes sense. Right? So simplify, right? Try and simplify. So if it's a radical, you rationalize. If it's some quotient and it's giving you infinity minus infinity, you simplify by writing as a single like fraction and so on. It depends on the kind of question you get, right? Yeah, but you get something like this on your exam, I should say. Yeah. Please, any questions here? That's the end of 2.6. Anybody needs time? Do I see a chat? Okay, so then let's go. Oh wait, I see something. So if the pies are flipped, perfect. If the pies are flipped, like s minus s squared, then the s squared will be increasing faster than the x. So that'll be what? That one will approach infinity faster. So that'll be negative infinity. Yeah, you see it. Yeah, perfect. Okay, so let me close this, save. What's the time? 42. So at least we can start 2.7 today. Okay. Let me share. I'm sharing 2.7. If you can't see, do let me know. 2.7. Wait, did I see something in the chat? Okay, no. So now in 2.7, now the 2.6 is just the last bit of limits that we've learned, right? Don't forget, when we started this class, we looked at 2.1, and then we're dealing with the tangent problem, and then there was the velocity problem. That was what led us to trying to shift our focus to limits, because we realized that the tangent problem and the velocity problem are all limits. So we went to master limits. Now we are back. We are back to that same problem, right? We are back to the set of problems, like the tangent problem and the velocity. Now we are masters of limits now. So we are back. So that's 2.7, right? So derivatives and rates of change, right? So this is just drawing our attention back, like from 2.1, right? We were finding the tangent line to a curve and the problem of finding velocity. We realized that they involve the same type of limit, right? They were the same. As I said, the velocity problem, the instantaneous velocity is equivalent to the slope of the tangent line. And then the secant slopes are equivalent to what? The average velocities. So they are the same. It's just the same thing they're doing. Now, because this thing occurs in the same, this kind of limit idea occurs the same under the tangent problem and the velocity problem, and even for several other kind of functions, because we know that it reoccurs in several fields, we just needed a single name for it, right? We just needed a single name. So we are trying to call that limit now as a derivative. So that special type of limit which is involved. So the limit of secant lines, the limit of secant slopes, and then the limit of average velocities, they are all the same ideas, right? It's just a change in the function name. So because you know they are the same, we are calling it a single thing now. We call it the derivative, right? And later on, we see that it's not just under these two problems. It's also under something called rate of change, which occurs in natural and social sciences. So let's go back to the problem that we started with, the tangent problem. So for tangent problem, right? So this is just a recap. So for tangent problem, we were looking at y equal to f of x, right? This was the function notation of a curve, and then we wanted to find the slope of the tangent at what? A point P A f of a. Like you remember this, the tangent problem, right? So we wanted the slope at this point. So we concluded that we can't find the slope because there's just one point. So to get other points, we said, okay, let's try secant lines, right? So we found the slopes of secant lines. And for the slope of secant line, we let the secant line pass through this point and then some other point on the curve, which we called Q, right? If you recall. And we said for any other point Q, it's just the coordinates are x and then f of x, right? So we went on to find the slope of this secant lines, right? What was the slope? The slope can be computed as change in y over change in x. So for MPQ, this is the slope of the secant line, right? The slope of secant line. Slope of secant lines. We said that that one is just going to be what? F of x minus f of a over s minus a. How did we get this, right? Remember that we compute the slope by doing rise over run, right? So s2, y2. So if you have your y2 minus y1 over s2 minus x1, then it's just simply y2 will just be f of x, your y1 will be f of a, and then your s2 will be x, and then your s1 will be a. So that's how they are getting this. So this represents the general formula for the slope of any secant line that we can think of. Please, are you okay with this? This is just a recap of what we did in 2.1. Any questions here? Anybody needs time here? Okay, so you are developing the formula now. So after getting that, right, so the blue lines are the secant lines, right? So after getting the secant lines, we move them closer and closer to this P point, right? Because we were interested in the tangent line, which is the red line. So we move closer and closer. So if this point is A, as you can see here, right? And then any other point on the secant line is just X. We let the X get closer to the A. So this one is the S approaching the A from the right, right? So we let it get closer. And you saw that the slope of the secant line becomes close to the slope of the tangent line as we let it get closer. Now we can do it from the right or from the left, right? We saw it in 2.1. So either from the right or from the left. This is the idea. In the long run, we are using this limit, right? We are letting X approach the A of the secant lines, right? So now we know we've established the formula for the slope of the secant line using the what? The slope, the limit of the slope of, we've established the slope of the tangent line using the what? The limit of the slope of secant lines. So this is the final formula, right? So the tangent line to the curve y equal to f of x at the point P, A, f of A is the line through is the line through P with the slope m equal to the limit as s approaches A of f of x minus f of A all over s minus A, right? Provided that the limit exists. So we saw that this one is what? This one is the slope of the tangent line now. Please, are you okay? Yeah, and if you don't get anything from this section is just about one formula. This whole section is going to be a lot, but all of them are just describing one formula. That's all you need to have in mind, right? Just one formula. We now have a formula for what? The slope of the tangent line now, expressed as what? Limit, a limit. That's the idea. That's the whole idea for this section. Okay, please, anybody needs time here? I hope you agree with this limit idea. Or do you have questions? Okay, but it's not the final formula you'll be using though. Anybody needs time here? Right, so if you are memorizing, don't memorize this. I'm going to give you the one that we're going to memorize. Okay, so now let's go back to the question. This is the same question we saw in 2.1, right? 2.1. It says find an equation of the tangent line to the parabola. I see something in the chat. Oh yeah, that's true. 2x close. Okay, that's true, Hunter. Yeah, that's true. But let's do this like using the techniques we've developed up to this point, right? So it says find an equation of the tangent line to the parabola y equal to s squared at the point P11. Let me see where the, okay, so there's no space here. Let me go to the whiteboard. So there's let me use a new slide. There's 2.7, example 1. Is it time yet? Let me check. Oh, almost. Okay, so let me just start. When it's 50, I'll pause and then we continue another time. So what did we say? Okay, so for this one, we know we are trying to find the equation of the tangent line, but then we have just a point. So what do? We just said that the limit, the slope of the tangent. What is this? What is the formula? As I said, don't memorize this yet. I'll give you the one that you have to memorize. Okay, 1150 is this. Okay, let me see. Okay, so I'll end here. I think it's fair I end here, right, on the example 1. So we'll continue with this example the next time we meet. Thank you for your time. And please start looking at the study guide for the exam, right? So feel free to also send me an email if you want to meet. If you don't understand anything, please don't wait. You can even schedule an appointment for preparing for the exam, right? So whatever works for you, right? All the best. Let me know if you need help. And then see you on Friday. You have a quiz tomorrow, so please don't miss recitation. Okay, that's it. Thank you.
Thank you.
All right. Have a nice day.
Same to you.
Thank you.
You're welcome. I don't, Brandon, for the review during the class, I'm not sure. But for sure, on Tuesday, you have like a review. The exam is on Wednesday. But for sure, the class is not meant for the review necessarily. Right? The review will be Math Center, and then the TAs will also have it. But then you can also schedule like a side appointment. If you don't understand any question, I'll take my time, meet you anytime that's convenient for you, and then go through it with you. Right? So that one will, that's how it's going to work. But the class time itself is a given. If you're able to finish what you have to do, and we have some time before the exam, then I'll do some review in class. But I won't even be able to solve a lot of questions because just 15 minutes and I have to lecture and then solve those kind of questions. So maybe I'll solve one or two, but a lot of them will be on recitations and like Math Center review. And if you want to schedule office hours, yeah. Okay, you're welcome.
Hey, Matthew,